Today, I would like to talk about change of basis, which is also known as change of coordinates. We will talk about what this actually means and why we would want to do this. Changing bases can greatly simplify problems, as we will see in an example which is towards the end of the video. Before we start switching between bases, we need to properly define what we actually mean by a basis. We define a set of vectors to be a basis of a vector space if it satisfies the following properties. The vector space is spanned by the vectors in the set. This means we are able to get any vector from the vector space and write it as the sum of scaled multiples of the vectors in the set. This is also known as a linear combination. These types of sets are called generating sets because you can think of them as being able to generate the whole vector space just by taking linear combinations of the vectors in the set. The second condition is the set of vectors is linearly independent. We want this because we want the coefficients of the linear combinations to be unique. This will be important later when we get to coordinate vectors, but how does the set of vectors being linearly independent guarantee that the coefficients of the linear combinations will be unique? I will actually go through the proof for this because I think that it is quite clever. We let beta equal v1 through vn be a basis of the vector space V. Recall that a set is linearly independent if the only way to write the zero vector as a linear combination is to have the coefficients of each vector be 0. Now we consider a vector s in the vector space. Since we assumed beta is a basis of V, we should be able to write s as the linear combinations of the vectors in beta. So let's suppose there exists an s equals b1 times v1 plus all the way up to bn times vn. We can subtract the second equation from the first one. Combining like terms, we get that 0 is equal to a1 minus b1 times v1 plus all the way up to an minus bn times vn. But beta is linearly independent, so by definition, all of the coefficients are equal to 0. So a1 equals b1 all the way up to an equals bn. This shows us that the coefficients are the same, which tells us the representation is unique. If we write a vector as a linear combination of basis vectors, all of the information of the vector is contained within the coefficients. But right now, if we were just given the coefficients, we wouldn't be able to tell which vector we're talking about, because we didn't define a specific order to the vectors. This motivates us to define an order to our basis. So, a list of basis vectors with a defined order is called an ordered basis. From now on, whenever I say basis, I will be referring to an ordered basis. Now, we can use this to define coordinate vectors. We define a coordinate vector as a vector containing the coefficients of a linear combination required to get that vector, with respect to a specific basis, which will be written like this, where beta is the basis. This will be known as the coordinate vector with respect to beta. You will also hear this referred to as a vector in beta coordinates. Coordinate vectors will be unique because, as we proved earlier, the coefficients of the linear combinations will be unique for a specific basis. Let's do an example. Suppose we are working in R2 and our basis beta is 1, 1, negative 1, 1. Let's pick the vector 10, 4. This can be written as 7 times the first basis vector and negative 3 times the second basis vector. So the coordinate vector for 10, 4 with respect to beta is 7, negative 3. Now let's do this again, but with another basis, gamma, 4, negative 2, 3, 3. Since 10, 4 is equal to 1 times the first basis vector and 2 times the second basis vector, the coordinate vector of 10, 4 with respect to gamma is 1, 2. These both are coordinate vectors of the same vector, but with respect to different bases. How do we go about switching between these bases? We want to find a matrix which lets us transform between the different coordinates. To be able to find the matrix which lets us switch between bases, we need to prove the following about coordinate vectors. First, the coordinate vector for x plus y equals the coordinate vector for x plus the coordinate vector for y. We also want to show that the coordinate vector for cx, where c is a scalar, equals c times the coordinate vector for x. These properties will help us in finding the matrix, so now let's prove them. First, we let beta be a basis of V, and x and y be vectors in V. Let x be a1 times v1 plus all the way up to an times vn. So the coordinate vector for x in beta will be a1 all the way up to an. Similarly, let y equal b1 times v1 all the way up to bn times vn, which means the coordinate vector for y in beta will be b1 all the way up to bn. So we can add and combine like terms, so the coordinate vector for x plus y is equal to a1 plus b1 all the way up to an plus bn, which is the sum of the coordinate vectors for x and y. Now, we will prove the coordinate vector for cx will be c times the coordinate vector for x. If we have x equals a1 v1 plus all the way up to an vn, the coordinate vector for x in beta will be a1 all the way up to an. Then, if we multiply both sides by c, we would get, so the coordinate vector for cx will be ca1 all the way up to can, which is just c times the coordinate vector for x. Suppose we have a vector space V with two bases, beta and gamma. Let x be a vector in V. Let x equal a1 times v1 all the way up to an times vn. So its coordinate vector with respect to beta will be a1 up to an. Now, we need to find the coordinate vector for x in gamma. This will equal the coordinate vector for a1 times v1 plus all the way up to an times vn. Now, using the property we proved earlier, we can split this up. Using the second property, we can take the scalars out of the coordinate vectors. We can write the following as a matrix vector product. So the matrix will have columns which are the coordinate vectors for the basis vectors from beta in gamma coordinates. The vector a1 up to an is the coordinate vector for x with respect to beta. This is exactly what we were looking for. We can take the coordinate vector with respect to beta, multiply by a matrix, and get the coordinate vector with respect to gamma. Let Q represent this matrix. We will add beta to gamma to show that if you have a vector in beta coordinates on the right, it will switch it to gamma coordinates. But how would we take a coordinate vector in gamma and translate it to beta? If we multiply by the inverse of this matrix, we will be able to convert from gamma coordinates to beta coordinates. Let's make this all more concrete by doing an example. Let's consider the example from before, where the vector space is R2, beta is 1, 1, negative 1, 1, and gamma is 4, negative 2, 3, 3. We will be converting from gamma coordinates to beta coordinates. So, we need to find the basis vectors of gamma in beta coordinates. 4, negative 2 is equal to 1 times 1, 1, and negative 3 times negative 1, 1. So 4, negative 2 in beta coordinates is 1, negative 3. Similarly, we can find 3, 3 in beta coordinates to be 3, 0. We can put these in our matrix to get 1, 3, negative 3, 0. From our example from before, we know that 10, 4 will be 1, 2 in gamma coordinates. If we multiply this vector by our matrix, we get that 10, 4 in beta coordinates will be 7, negative 3, which is exactly what we calculated previously. If we have a matrix in beta coordinates, how would we do the same transformation in gamma coordinates? Let the transformation in beta coordinates be called A. What we can do is switch from gamma coordinates to beta coordinates, do the transformation, and then switch back to gamma coordinates. By sandwiching the transformation between two change of basis matrices, we can do the transformation in gamma coordinates. But why would we ever want to do this? Well, if we are clever about the bases we choose, it can greatly simplify a problem, as we will see in our next example. Suppose we have a matrix A, 4, negative 1, negative 2, 3. We start at 1, 1, and we want to see what vector we would get if we applied the matrix 25 times. We can do this by multiplying the vector by the matrix to the 25th power. Multiplying this matrix 25 times will be a pain, so we want to see if we can switch to a basis which makes this easier to compute. Let's look at the transformation, but focusing on the vectors 1, 2, and negative 1, 1. As you can see, before and after the transformation, they are on the same line. So repeating this transformation will just scale these vectors. This motivates us to use these vectors as bases, repeat the transformation there, and then translate back to our original basis. Let alpha be the standard basis 1, 0, 0, 1, and let beta represent the basis 1, 2, negative 1, 1. So our matrix A should equal the change of basis matrix from alpha to beta times some matrix D times the change of basis matrix from beta to alpha. Let's start by finding the change of basis matrix from alpha to beta. This will be the matrix which has the columns that are the vectors from beta in alpha coordinates. 1, 2 in alpha coordinates is just 1, 2, and similarly negative 1, 1 will just be negative 1, 1. So the change of basis matrix from alpha to beta is 1, negative 1, 2, 1. Now, we need to find the change of basis matrix from beta back to alpha. Like we discussed previously, this will just be the inverse of this matrix. Now, we can use these matrices to solve for D. Since A equals Q dQ inverse, we can multiply by Q on the right, and then by Q inverse on the left. So, Q inverse AQ is equal to D. Working through the computation, we get that D is equal to 2, 0, 0, 5. D is a diagonal matrix, which means it only has entries along the diagonal and zeros everywhere else. Another thing to notice is what happens when we multiply the matrix by itself. D squared is equal to 4, 0, 0, 25, which is just 2 squared, 0, 0, 5 squared. This holds more generally for any n. Now, we want to see what a to the 25th power is. Let's start by seeing what a squared is. But in the middle, there's q inverse times q, which just equals the identity. So a squared is just equal to q d squared q inverse. You can convince yourself that this pattern will continue for higher powers of a. So a to the 25th is just q d to the 25th q inverse. Working this out, you get the following matrix, which we can multiply by our original vector to get our final answer. So, there's an example of how changing the basis simplified a problem greatly. You might be wondering, is it always possible to diagonalize a matrix? And the answer is no. There's a way to tell if a matrix is diagonalizable by looking at its eigenvalues, but that is outside the scope of this video. If you are interested, I recommend you do some more research and look more into eigenvalues and diagonalizable matrices. It is truly fascinating. Next time, we will be covering orthonormal bases and the Gram-Schmidt process. See you then!